In the last class, we discussed the Reynolds transport equation. We derived the mass conservation, momentum conservation and energy conservation equation. So, those equations I will write it down here. The material derivative of any property is the time variation of that property within the control volume plus the convective part, or the property that is coming in and going out of the control surface. If the property is mass, we have seen the value of eta is 1. Control surface rho into V dot dA. If the property is the force, it is essentially sigma force as the eta is now take the velocity as 1 plus the control surface V rho V cross dA, and if it is energy, we have seen dE by dt as dou W by dt integral CV. The total energy per mass rho into dV plus control surface total energy per mass rho V dot dA. And we have also substituted this in the second law of thermodynamics, and we have obtained this as dq by dt minus dw shaft by dt equals dou Wt by del E rho dV plus integral control surface E plus PV. V is the specific volume V into density into V dot dA. Okay. Now, we will try to understand these equations further. So, and we will try to do some examples and try to get a feel of these equations. Okay. So, I have a question here. So, I have a long pipe which is going into a cylinder. Okay. So, this pipe has a pressure of say 10 megapascal. Okay. And the temperature of around 400 Kelvin. Okay. Let us assume air. So, your gamma is 1.4, your Cp is 1005 joule per kg Kelvin. Okay. Now, the gas goes into the cylinder, there is a valve here, okay. The valve opens and the gas flows in. So, the pressure moves from 0 to 10 megapascal. So, when it reaches 10 megapascal, the valve automatically closes. Okay. So, what would be the temperature inside? Okay. How do we apply this equation to this problem? Okay. For this thing, first we have to identify the control volume. So, our control volume is the cylinder. Okay. I am redrawing that here. So, this is in and there is no outlet. So, there is just one inlet. So, I apply the energy equation or the conservation of energy equation from the, so application of Reynolds transport into the second law of thermodynamics will give you this result, which we have derived in the other class, last class, and we are going to apply this there. Okay. So, dq by dt minus dws by dt. So, dw by dt contains two components, one is the shaft work done and the force done by the surroundings to push the air into the control volume. Okay. So, that is the PV which we have seen in the last lecture. So, dou by dou t integral control volume E rho dV plus control surface E plus PV rho V dot dA. Okay. Now, let us assume there is no heat transfer, there is no shaft work. Okay. So, your Q addition is 0 and shaft work is 0. Okay. So, these two terms vanishes. Okay. So, if these two terms vanish, what is left here is and your E is U plus V square by 2 plus Gz into rho dV plus control surface U plus V square by 2 plus Gz plus PV into rho into V bar dot dA equals 0. Now, if the gas is leaking, if the gas leaks into the cylinder or if the gas slowly fills, the velocity into the inlet crossing the control volume is 0. So, you could assume okay, or your kinetic energy is assumed 0, and you can also assume your potential energy to be 0, okay, which essentially means this term is 0, this term is 0, okay. So, you are left with dou by dou t triple integral internal energy rho dV plus h into rho v dot dA. Okay. Now, this is the internal energy per unit mass, which means that this is d by dt of your full mass. So, u is nothing but your small u into m dot. Okay. Maybe I will rub this. Plus there is only one inlet. So, this is the only inlet. So, you have H inlet into your m dot inlet. Now, this is something that is going into the system. So, you could write this as a minus sign. This goes into the system, which is minus sign, okay, equals 0. All right. So, that is the balance of energy that is crossing this inlet and filling this control volume. Okay. Now, the same set of analogy for the mass conservation would give me mass that is going into the control volume minus my m inlet. Okay. So, that is my equation 2. So, I substitute equation 2 in equation 1. So, my du by dt minus h inlet into dm by dt equals 0. Okay. So, that is the balance of energy equation that is happening inside the control volume. Now, at time t equals 0, your pressure is P0, P equals some value. At time t equals some T1, your pressure is 10 megapascal, at which time the valve closes. Okay. So, it is from state 1 to 2, state 1 to state 2. So, the system goes from state 1 to state 2 in time T1. So, you are actually integrating between 1 and 2, the whole set of equations, okay, which will give me u2 minus u1 equals h inlet into m2 minus m1. Okay. So, the enthalpy of the fluid that is crossing this control surface is always the same, because you have a constant supply of 10 megapascal 400 Kelvin gas. Okay. So, that is always constant. So, U2 is small u2 into m2 minus small u1 into small m1 H inlet into m2 minus m1. What is m1? m1 is the gas at T equals 0. So, the gas at mass of gas at T equals 0 is your m1, which is 0, because initially the cylinder was empty, which means this is 0, this is 0. So, your U2 m2 equals H inlet into m2. So, now you have a simplified equation for this case which we are discussing, which is U2 equals H inlet. Okay. What is U2? CV T2, H inlet is this value, which is your Cp set T1, or Cp, Cp temperature at the time when the gas pressure is 10 megapascal inside the cylinder, and this is the temperature at which the fluid is crossing the control surface. So, your T2 is nothing but gamma into T1, which is 1.4 into 400. Okay. So, that is your okay. So, that is how you apply these equations to this flow. We will have a few more problems. Okay. We will drop this. I will discuss question 2. I have a long pipe. Okay. So, the fluid is going from station 1 to 2. The pressures P1, T1 and V1, P2, T2. So, let us put 150 kilopascal some T2 is okay. So, I have a long pipe between station 1 and 2. I have to evaluate my velocity change. So, I have pressure P1, T1 and V1 at location 1 and pressure and temperature at location 2, what is your V2? So, mass conservation equation is of the form rho 1 A1 V1 equals rho 2 A2 V2. Your area is same. Okay. Okay. So, it is rho 1 V1 equals rho 2 V2. Now, how will you find rho 1? You could use your ideal gas equation, which is P1 by R T1 into V1 equals P2 by R T2 into V2. Okay. So, you know all these quantities P1 T1, P2 T2 and V1, from which you could find your V2. Or you could use the energy equation, which gives me H1 plus V1 square by 2 plus Q equals H2 plus V2 square by 2 plus Ws. If Q equals 0 and W is 0, I could write this as Cp T1 plus V1 square by 2 equals Cp T2 plus V2 square by 2. From which you could find your V2. So, if it is a different gas other than air, you use the appropriate value of the Cp and you find your V2. Fine. So, we will go to the next So, I have a chamber, I have a pressure and a temperature here, say some 200 degrees Celsius and say 10 kilopascal. The example I have is 300 kilopascal. The mass that it contains is so let us say 8 kgs. Now, the chamber is heated till pressure reaches 400 kilopascal. Okay. Now, find your T, find the Q required to heat this chamber to the pressure 400 Kelvin, find your entropy change. Okay. So, how do we do this? First we identify the process is constant volume process. Okay. So, the ideal gas equation P1 P equals PV equals RT. So, at between state 1 and 2, this would become P1 by T1 equals P2 by T2. So, now you have P1, now you have P2, you have T1, find T2. Okay, so, P1 is 300 kilopascal by 200 plus 273 Kelvin equals P2 is 400 kilopascal divided by T2. So, you can find your T2. So, what is Q? It is a constant volume process. So, your mass into CV into delta T. So, mass is 10 multiplied by the appropriate CV into T2 minus T1. So, that should give me the mass, the heat that is supplied in joules. This would be in Kelvin. Okay. Now, what about delta S? CV ln T2 by T1 minus R ln V2 by V1. Is this a minus or plus? It is a plus. Okay. That is the specific entropy change. So, if you want the total entropy change, you multiply this with M, which is ln T2 by T1 plus R ln V2 by V1. Okay. Since V2 by V, it's a constant volume process. So, this would get cancelled. So, what is left here is this. So, since V1 and V2 are same, this would cancel out, and what is left is this. So, that would be your, so M is 10, appropriate CV ln, yeah, whatever value you get for T2 plus T1. Okay. I have a constant area duct, kept isothermally. So, I have fluid that is going in. So, the pressure at 1 is (200 kilopascal) and the fluid goes to station 2 where the pressure is, say let us say 50 kilopascal. Okay. What is the velocity at station 1, velocity at station 2, what is the Q change? Let us say so you apply your energy equation. So, you have one exit and one entrance. So, your energy equation is H1 plus B1 square by 2 plus Gz plus Q equals H2 plus V2 square by 2 plus Gz2 plus Ws. So, there is no datum change. So, Z1 minus Z2 is 0. There is no shaft work. So, Ws is 0. It is an isothermal process. So, your Cp T1 is same as your Cp T2. So, those two terms will also cancel out. So, your Q is nothing but V2 square minus V1 square by 2. Okay. Now, what is V2? You could use the mass conservation equation to area cancels out. So, your V2 is so your rho 1 you substitute from the ideal gas equation P1 by RT1 is your rho 1 B1 equals P2 by R T2 into V2. T1 and T2 are same. So, this cancels out. So, you could get V2. You know P1, you know P2, you know V1. So, V2 can be evaluated in meters per second. Substitute that in here, you would get your heat change. Okay. Now, if the same system is vertically up, going from 1 to 2, P1 is same, P1 is 200 kilopascal and P2 is 50 Pascal. The same problem except that there is a datum change. So, what do? You have to include the datum change also, the potential energy change. So, your H CPT1 plus GZ1 plus V1 square by 2 plus Q equals CPT2 plus GZ2 plus V2 square by 2 plus WS. So, WS is assumed 0, CPT2 and CPT1 are same because the temperature is same because it is an isothermal condition. So, you are left with Q is V2 square minus V1 square by 2 plus G Z2 minus Z1. So, you need the distance between these two. So, let us say that is 10 meters. So, V2 you can get it from the same process, we have not used anything here, it is just the mass conservation and the ideal gas equation, these two are going to be the same. So, the V2 is going to be same. So, this quantity is going to be same plus some addition. So, that would be your, so potential, if you have a potential, the heat exchange is going to be this much. Okay. Now, let us look at something similar. So, what we are discussing here is just the mass conservation and the energy conservation and the momentum conservation. So, these are some of the examples, some of the areas where you could apply these equations which we had derived in the last class. So, another location or another case is something called rocket engine. Say suppose you have an oxidizer here, you have a fuel here, this goes into a rocket engine. Okay. So, the oxidizer is pumped into the rocket engine at some mass flow rate, and the fuel is again pumped into the engine at some mass flow rate. You have to find what is the exit velocity. Okay. So, this would be your control volume. Okay. So, the control volume is your rocket engine. So, you have 2 inlets and 1 outlet. So, the mass that is going in should go out. So, the mass of O2 plus mass of fuel should be your mass that is going out of the exit. So, you apply your so if you know your velocity with which it moves in or the density, the area of the nozzle exit. So, if you know area of the exit and the density at which the fluid is coming out of the nozzle, you could find the velocity of the exit. So, you could put numerical values to these quantities and do the problem yourself. So, I think we will stop this tutorial lecture with this. So, so what we have discussed this week is the thermodynamics, applying the second law of thermodynamics to the Reynolds transport equation. Then applying the Newton's law to the Reynolds transport equation, we derived some equations, energy equations and the mass conservation equation. We applied that to some of the cases that we know of. So, you could expect similar problems, similar numerical problems in your assignments.